So what we are going to do today is, why it is not being shared. Yeah, we'll first solve few questions based on the impact of jets problem. So I hope the screen is visible to you. So let us first read the question and then we'll solve this. This is one of the question appeared in the GATE exam. So it says that there's a 60 mm diameter water jet, 60 mm diameter water jet strikes a plate which contains a hole of 40 mm diameter as shown in the figure. So this diameter is 40 mm it says, and then it says that the part of the jet passes through the hole horizontally and the remaining is deflected vertically, and it was expected. Yes, we have seen now then when it was the flat plate, then jets strike and it was deflecting like this one. Yeah, but here what happens that there is some hole. So so what happens that some of the fluid will pass through that hole and other will get deflected. So this is what the question says. And then it says that the density of water is 1000 kg per meter. These are as indicated in the figure. Velocity is also indicated. And it says the magnitude of horizontal force in Newton required to hold the plate. So how did we use to find out this in this case? See, they have not mentioned that plate is moving or anything. So it says that somewhere it must have said remaining deflected vertically. Okay, there's no velocity thing, right? That means that I will assume that plate is stationary. So in case of a stationary plate, if you remember what was the formula was rho q va square, if we remember, m dot into v2 minus v1, not v square, rho q v2 minus v1 means rho q into v. So initially the formula was, if there was no hole, then the formula was m dot into v2 minus v1, and this, since there is v2 is 0, that means that this is m dot v1 if I talk about magnitude. So what is m dot now? M dot is rho times area into velocity and this velocity. So this is v1, this is also v1. So this is rho a v1 square. But what is the problem here? The whatever was the mass coming at this point, but only few of them is striking and few of them is getting passed out. Can we see that? So what will be the mass flow rate which is striking out, which is striking it, that will we will have to find out. Then only, why? Because this was the mass, this was the mass flow rate, this was the mass flow rate which was entirely attacking this plate if there was no hole. But since there is some hole, that means this much mass will get passed through this hole. There will be no attack by this mass, so we'll have to take care of that mass which is not attacking it, rather passing it. So here only thing you need to do is that you need to make change in the mass flow rate. And what will be that mass flow rate? Here mass flow rate is rho a v1 square. No, mass flow rate is rho a v1 only now. So what is mass flow rate which will strike it is rho, area is pi by 4 into 0.6 centimeter, means 0.06 whole square, 60 mm, and minus pi by 4 into what, 0.04 square into 0.04 square. This is the mass, this is into velocity. Velocity is given as 20. So this is that mass, this is that mass which is striking. Why? Because this much was initially coming and this is initially going out. So the difference between these two is striking the plate. So first thing we need to do is that we'll find out the mass flow rate. So I'm doing final now, that mass flow rate which is striking is density times velocity into area, and area pi by 4, let us take common pi by 4. So here we are left with 0.0 whole square. Now what will be that force? Force was m dot into v, and v velocity is again given as 20, where value is 20. So m dot you find out from here and put that value here and you will get that force. Okay. Are you calculating? This was easy, right? Here. Yeah, 628.318 is okay. Okay. So let us move to the next. Simple now. Just stick to the basic. I told you now that what was the funda, that whatever mass which is striking, take care of that. And we here there was some hole, so that mass is not striking it, rather passing it. Just one concept, and we are done. So let us move to another question. Let us read this question. It says that there is a cylindrical jet of water and density 1000 kg per meter cube. It impinges at the center of a flat circular plate. There is a flat circular plate and it is impinging it centrally and it is being spread out radially. Fine, as shown in the figure. Then it says that the plate is resting on a linear spring with the spring constant K is 1 kilonewton per meter. And then the incoming jet diameter d is given 1 centimeter, means this diameter is given as 1 centimeter. Okay, now it says that if the spring shows a steady deflection of 1 centimeter upon impingement of jet, it says that when this jet strikes this cylindrical plate, now this is spring attached, so this spring gets deflected by 1 mm, 1 mm was 1 centimeter, sorry, 1 centimeter. Then it asks you to the find out the what is the velocity. So it's again very simple. What happens here is that when there is jet, when there is jet, then this jet is striking some force upon it, yes or no, some force upon it. And since it is attached to a spring, that means that force is transmitted to this spring, and this spring is deflected by 1 centimeter. So do we know that what is the force in spring? Force in spring is spring constant k times whatever is the displacement x. So k value is given to us as 1 kilonewton, so let us convert it into newton. So this is 10 to the power 3 newton per meter, and x, the displacement value, is given as 1 centimeter, so this is once upon 100 meter. So this and this got cancelled, so your force value is nothing but force in the spring is 10 newton. Okay, so your force in the spring is known now. Okay, so this force is that this force this spring force, this spring force 10 Newton is due to whom? Due to this jet. Yes or no? Due to this jet, there is some force. So what you will do now, that this force we knew that this is density times area of the jet into velocity square. So can you solve now that this is 10 Newton, this is equal to density 1000, and what is that area? Area is pi by 4, pi by 4 into d value is given to us 1 centimeter. So 1 by 100 whole square, 1 by 100 whole square multiplied by velocity, this we need to find out. So velocity whole square, when you will solve this one, then you will get the velocity value. I hope all of us are getting. So this value will be somewhere around 11.3. When you will solve this, velocity will be 11.3 meter per second. Okay, not meter per second square. Velocity is in meter per second always. Okay, okay. Let us solve quickly. It says that there is a Pelton wheel whose bucket peripheral speed. So the meaning we should catch. Bucket peripheral speed is 10 meter per second. So it says that u is 10 meter per second. Okay, and then it says that the water jet velocity is 25 meter per second. 0.1 meter cube per second. If the jet deflection angle is 120 degree and the flow is ideal, then this is power developed is means what is the power developed. So what things are given to us? Let us first write down the u value is given as 10 meter per second, and moreover this is all about Pelton wheel. So u value we know 10 meter per second, then we are known with discharge is 0.1 meter cube per second, and then we are known with what velocity v is 25 meter per second, and this velocity is nothing but v1. Yes or no? The water jet velocity is 25 meter per second, that means v1 value is also given to us. And what is more given to us? Deflection, that is delta value is 120 degree. So let us first try to draw the velocity triangle, then we'll be able to answer that what is the power developed. So in order to draw velocity triangle, we should know the prior concepts to draw it. And what was that? That this is attacking it tangentially, that means the v1 value and vw1 value is known. Okay, so I'm just drawing it out. So what was that? That this is v1, right? v1, this is given to us as 25 meter per second. 25 meter per second, and then u1 is given as 10 meter per second. 10 meter per second, then vw1, this is also equal to what? vw1, this is also 25 meter per second. So what is vr1 now? This is that vr1, right? So vr1 is equal to 25 minus 10, 15 meter per second. So till this point things are not. Then what we have at the exit is vr2. So this value is that VR2, and it says that flow is ideal. That means that this VR2 will be equal to VR1. This is also 15 meter per second, and we know that U1 is equal to U2. So this value we also know that this is 10 meter per second. And now what we need to do is that this is your absolute velocity at the exit, and but we need to find out what is this vw2, right? This is that vw2, this we need to find out. Why? Because we know that the power developed was, we know that this was rho q vw1 u1, or vw1 plus vw2 into u. So vw1 is anyway known to us, yes or no? Yeah, here vw1 is known, so we need to find out what is that, what is the value of vw2. Okay, so this angle is given to us, this angle is given to us as, this angle is given to us as 120 degree. So this is 60 degree. So if this is 60 degree, then this is also 60 degree. Yeah. So now we need to find out what is this vw2. Vw2 value, how we will find out? What are the guesses what we can do to find out vw2? Tell me. That vw2 will be what? That vr2 cos 60, vr2 cos 60, vr2 cos 60 minus 10. Please do that. 15 cos 60, 15 cos 60 minus 10. What is this value? 15 cos 60 minus 10. Please do that. What is 15 cos 60 minus 10? 15 cos 60 minus 10. 1.5. Okay. So this is not 1.5. This must be 2.5. 2.5, right? So this is 2.5 and minus 2.5. So what we will do that this is in this direction. So initially what we need to do is that this will get added. So rho value is 1000, q value is given as 0.1, and vw1 is given as vw1 is given as 25, as 2.5, multiplied by u is given as what, 10. Please do this one, the calculation, and then you will get the answer. No, see, vw2 value we have got negative, right? So this negative value shows that the velocity triangle is not like this one. I will show you the modified velocity triangle. Here initially this will be minus vw2, this will be minus vw2. So the answer will be 22.5, 22.5 kilowatt. If you convert it into kilowatt, then this will be 22.5 kilowatt. See, I am redrawing this velocity triangle. See, what happened here is that vr2 vr2 cos 60 is lesser than vr2 cos 60. This value vr2 cos 60 is lesser than 10 meter per second. That means your velocity triangle would look like this at the exit. Yes, I should draw. See, here I am drawing. See, this is vr2 and this is u. This is u, which is 10, 10, and vr2 cos 60 is lesser than this one. That means your v is here. This is this is vr2 and this is v, and then this is u. So now what you can see is that the this vr2 cos 60, vr2 cos 60, can you see now that this vr2 cos 60 is less than u value? Vr2 cos 60 is less than u value. Why? Because this is u10 and vr2 cos 60, this value is 7.5. Okay, so absolute velocity, this one, so its component is in this direction, yes, and this component is vw2. So the vw2 direction is this one, and initial direction was also this one. So that is why here we need to use minus sign. Got it, why we are using minus sign here? Please tell me. See, sometimes in the books also you will see that the velocity triangle are drawn like this. What is that logic? That you will have to check that this vr2 cos 60 or cos 5, we denoted it by 5. So what is the magnitude of vr2 cos 5? If it is less than u, the velocity triangle will be this. If it is greater than u, the velocity triangle is like this. Okay. And one shortcut yesterday we have seen, the formula was directly reduced to what? That power was rho q into v1 minus u into 1 plus cos phi into 1 plus cos phi. Phi. Okay, multiplied by u. So this formula yesterday we saw, right? So using this formula, we can again reduce to the power, or otherwise, conceptually we can do it. Like there is no need to mug up the formula, we can use it conceptually also. Okay, moving to the next question. See, this question we can just solve it using our brain. Like there is no need to know this one, the concept of this. What is the turbine? Whose velocity triangle is given? Nothing. Just read the question. That is why I have taken that. Sometimes what happens that even though you don't have much idea, now you can solve the question. See what it says. It says that there is the at inlet of an axial impulse turbine rotor, the blade linear speed is 25 meter per second. So blade linear speed is given. So blade linear velocity 25 meter per second is given. The magnitude of absolute velocity is 100 meter per second, means at the inlet v value is given, that is v1 value is given, and u1 value is also given. Then it says that the relative velocity, mind the word relative velocity, and the axial component of velocity remain the same between the inlet and the outlet of the blades. So what does it mean? That if this is V1, this is U, then this is bound to happen VR1. Yes or no? Why? Because the velocity triangle, how V and U gets close using VR1, right? Similarly here, what do have, this is VR1. Why? Because it says that the velocity remains same. Yes or no? Relative velocity remains same. So if I consider this one as inlet, then this is VR2. Okay, and then if this is vr2 and this is equal to u2, then this is bound to happen v2. Yes, so I know v2, I know u2, I know vr2, I know VR2. So now I know most of the things, that V1 I know, VR1 also I know. So now what is the question? It says that the blade inlet and outlet velocity triangles are shown. So assuming no losses, it says that the specific work in joule per kg. Specific work in joule per kg. So how did we find out it? That rho times q into vw1 plus minus vw2 into u. Yes, this is how we will do it. Okay, what is vw1, what is vw2, u I know, and q, what I will do is that for q, do we have hint? If the q is not given, then I will consider this rho q value as what? This is nothing but mass flow rate, right? So this I will consider as unit, and it says that the per kg you find out. So I need to find out vw1 value, vw2 value, and u value. So let us see how we will do it. See, Vw1 is nothing but the tangential component of initial velocity. So can I write down Vw1 directly? This is 100 times cos 25, 100 cos 25. So this is Vw1, right? Okay. Now, what about Vw2? Vw2. So for Vw2, we need this angle. Yes or no? Then only we will be able to find out. For vw2 we need this angle, but there is no hint about this angle. But it says in the question that the axial component of velocity also remains same. So what is the axial component of velocity? Axial component of velocity, first one is this one, that is, this is 100 sine, right? 100 sine 25 degree is equal to, this is vf1, right? And it says that vf1 value is equal to vf2, is equal to vf2, and vf2 value is this one. So can I say that this is 58.6, 58.6, and let us say that this angle is alpha. So can I say that this is 58.6 sine alpha, but it says that vf1 is equal to vf2. So can I use this relation that 100 sine 25 degree is equal to 58.6 sine alpha? Using this concept, find out what is alpha. Tell me the value of alpha. This is 46.51 or 15. So this value is 46.15 degree. So once you know the alpha, then you can find out what is this, this component, means this component, right? Because we need the tangential component VW2. So what will be that? This is 50 VW2 value is 58.6 multiplied by what? Cos component, cos 46.15, right? So please do that. Cos 46.15 multiplied by 58.6. So this value is 40.6. This value is 40.6. So I know VW2, I know VW1. What is this value? 100 cos 25. This value is 90.63, right? This value is 90.63. So what is the final result now? This is rho q. So rho q is anyway 1. So now vw1 vw2, so vw1 is 90.63, so write down 90.63. vw2 is in opposite direction of vw1, so this will get added. So plus, and what is that value? vw2 is 40.6 into u value is given as 25. So this is that answer. Got it? So this value is 3280.76. Yeah, got it, everyone? Please tell me. See, if you kn- know only few concepts, still you were able to do. Even though there are lot many things, you might think that okay, I don't know this, but using the can solve. Yes or no? Only thing here change is that it is axial impulse turbine. So axial impulse means what? That it will have velocity components, that is flow component at both the points. Initially we have seen that when the it was tangentially acting, then we saw that there was no component, no velocity of flow component, no flow velocity component, or axial component was nil at the entry. But here we have axial component at entry and at the exit as well. Only thing you think after that what is given to you and how to utilize it, okay? And then we are done. Okay, so now let us move to what? Now let us move to reaction turbines. Reaction turbines. So, unlike Pelton turbine means impulse turbine, here we have both. Means initially we had seen we saw that we had only kinetic energy at the inlet, but reaction turbines, what do we have? Both reaction means pressure and kinetic energy at the inlet. Okay, so how do we solve such kind of questions? So before moving to that, let us first understand. I told you that here at the inlet, reaction flow turbines, first thing is that this is a radial turbine. This is the radial turbine, okay? And here water flows radially from in to out or out to in, okay? Is that in the reaction turbine we have water at the inlet which possesses kinetic energy at inlet. At inlet we have kinetic energy plus plus pressure energy as well. So initially what we saw that we were having only kinetic energy, but here we have some of kinetic energy and pressure energy at the inlet. That means your pressure, your water pressure is not at the atmospheric level but above the atmospheric level. That means your water flow or the flow of water through the turbine must be in a tight casing. Yes or no? Otherwise if it is exposed to directly to the atmosphere, then the pressure is not maintained, right? So in order to maintain that, what we are doing is that there is a very airtight casing inside which the turbine is kept and where flow is happening, okay? So during the flow means during the flow of means once the water strikes the veins and then it flows into that, right? So during that flow this pressure is again slowly get converted into what, get converted into kinetic energy. But since we have both at, things at the inlet, kinetic and pressure energy, so that is why it is called reaction turbines, because the due to the uh, means pressure, due to the pressure energy changes, this pressure gets converted into what, kinetic energy, okay? So essential components of reaction turbines are: first is casing, second is casing. I told you that this is a airtight chamber inside which the turbine is kept. Second thing very important is guide mechanism. Guide mechanism. And third thing is runner. These things we know na, runner we know. And very important part, that is draft tube. So casing we know, runner we know. Only thing we need to understand is guide mechanism. What is this guide mechanism? And draft tube, what are these things? See, what happens in the reaction turbines is, first thing is we have a very airtight spiral casing. Means there is a casing like this. Means not like this exactly, means so the curve, okay? And then here we have a spiral casing. Here we have runner upon which there is guide vanes and there is runner. Means this is the runner part, okay? And then we have guide vanes. So what is the duty of guide vanes? I will tell you. See, what happens is that here water is coming from penstock. So water from penstock is coming at this point, okay? So this water which is coming from penstock is entering this casing. This is that casing which I am talking about. This is that casing which I am talking about. So in this casing what happens, that this runner is not directly exposed to the water. Why? Because we have seen in the case of Pelton turbines also that the nozzle was, there was a nozzle fitted at the penstock end. Yes or no? So at the penstock end there was a nozzle fitted, right? So there was nozzle fitted. So similarly, what here we do have is that when water enters this casing, then we need some guide mechanism so that these waters are guided to these veins, to the runner veins, right? So these are those guide veins. These are those guide veins. These are those guide veins which will guide this water to the runner veins. So these are what? These are runner veins. Okay. So when the water are entering into the casing, they are going through what? These guide mechanism, and then they are directed to the runner veins. Okay. So this is called guide wheel. This is called guide wheel. This is called runner wheel. We already know that this is runner vane. So and this is that wheel, runner wheel. Okay. And this is the casing I am talking about, that spiral casing. Spiral casing inside which the flow is happening. Okay. Okay. So very important things about, let us and second thing is draft tube, right? Draft tubes. What is this draft tube? See what happens inside this what happens inside this spiral casing is that whenever there will be flow of water, whenever there will be flow of water, what will happen is that initially in the Pelton wheel, what we saw, that in the Pelton wheel, that at the inlet and at the exit of the turbine, we have at the inlet and at the exit of the turbine, at the inlet and the exit of the turbine, pressure was atmospheric. Pressure was atmospheric. But here we go, even what we do is that we keep on extracting the pressure from it, from the water which was coming from the penstock. So initially the pressure was too high, but when I kept on extracting pressure, then I reached at below the atmospheric pressure, below the atmospheric pressure at the end, below the atmospheric pressure, below the atmospheric pressure at the exit of the wheel. At the exit of the wheel means at that point your water is going to tail race. At that point your pressure is below atmospheric pressure. So now this cannot directly get exposed to whom? This atmospheric pressure which is below the which is the pressure which is below the atmospheric pressure, you cannot now expose this to directly to the atmosphere, otherwise there will be reverse flow, right? Why? Because your pressure inside the turbine is below atmospheric pressure, but at the outside the pressure will be atmospheric. So due to that difference, this is also called reaction turbine, right? This is why it is called reaction turbine also. Now let us understand one thing. Pressure is below atmospheric pressure, then we need to convert this pressure, whatever is at the exit of this turbine, to at least into atmospheric, so that we can drop it into atmosphere. So in order to convert it into atmospheric pressure, we have draft tubes. So we have draft tubes. So what is the job of this draft tube is to convert the low pressure into high pressure by reducing its velocity. Why? Because here we have velocity which is very high, so this velocity is reduced and the pressure is increased. So here at the exit of draft tube we will have atmospheric pressure, and then this can directly atmospheric pressure, and then this can be directly dumped into what? Tail race, or the directly into the water level, wherever it was. Okay. And and the velocity triangle, we know about it. Velocity triangle we have seen of the Pelton reaction turbines. Velocity triangle we have seen, right? So let us now quickly move to few more things, that how to tackle questions from this area, means the questions from reaction turbine. Okay. So let us talk few more thing about it. Is that can we see that in this case this diameter is different, means this diameter is different and this diameter is different. Can we see the difference? There are two diameters, one is this one and another is this one. So these two diameters are different. So due to these diameters, the velocity of the wheel, velocity of the wheel will be different. Will be different. That means u1 and u2, these two will be separate. Yes or no? Why? Because I can see that water is entering at certain diameter and exiting at another diameter. So the d1 and d2 values are different. Okay. And upon this, the blades are fixed, and they are fixed in which manner? Let me draw that. Okay, just a second. So what I am trying to do is that I am trying to show you the how blades are positioned. How blades are positioned. So this is the position of blade. Can you see? Can you see that the width at the entry? This is the point where the water enters. Okay, watering, and this is the thickness of the blades through which the water is flowing. I hope the blade profile is clear now. So this is like if this was the runner, center of the runner, then this is the diameter d1. Okay, and this is that diameter d2, and with respect to this d1 and d2 we have u1 and u2, and similarly at the entry we have some width that is called b1, the width of the blade. This is exit, we have certain width. This width I am talking about, this width. This is the width b1. Similarly, we have another width at this point. This is the that width b2. B1 and b2, two separate widths. Okay. So, what is the area of flow now? Area of flow, can I say that area of flow is nothing but pi times d, the perimeter, and whatever is the width. See, this pi d, if I know, and if I get it now, if I know the width, then pi d into b is that area of flow, pi d into b. So what is the area of flow at first point is pi d1 b1? Yes or no? Pi d1 b1. And what is the area of flow at 2? Area of flow at 2, this is pi d2 b2. Okay, and if t is the thickness of blade, this is the part I am talking about. This part, this is the thickness. Okay, so if t is the thickness of thickness of blade blade, then, and suppose the number of blades are n is number of blades, then what is the area of flow now? Area of flow, can I say that These are the areas which is not contributing into the flow, right? So what I will do essentially is, this is pi d minus n into whatever is the thickness, number of thickness times width at any point. At any point, what is the area of flow? Pi d is the perimeter times width will give the area. Yes or no? Perimeter times width gives the area, but n into t gives you what? That what is the number of blade and their respective thickness. So if I find out that what is the net area, perimeter multiplied by width, then I know the net flow area. Okay. Discharge, important term is, what is discharge? What is discharge? So discharge is pi times, or let us say that q is area of flow multiplied by velocity of flow. Okay, so area of flow just now we have seen is pi d into b multiplied by vf, pi d into b multiplied by vf. So can I say that, the if this discharge is to remain same, then I say that af1 into vf1 is equal to af2 into vf2. So can I write down that pi d b vf1 is equal to pi d b vf2? Yes, we can say that pi d1, or at notating as 1, so pi d2 b2 vf2. So if the velocity of flow is constant, if the vf is constant, why? Because at most of the time there is no flow, though no forces in the y direction. So what is the condition? That vf will remain constant, so vf1 is equal to vf vf2. So can I say one more thing from now, is that d1 v1 d1 b1 is equal to d2 b2 d2 b2, and I know that d1 is greater than d2, so that means d1 is greater than d2, that means b2 is greater than b1. Then only this equation will be equal to each other, that means d1 b1 is d2 b2. So that is why the this plate I have drawn like this, that here we have separate widths and here we have another width, and there is a lot of difference between these two. Why? Because this is at the bigger diameter, so width is less, and at the lower diameter width is high. Okay. Now, so now quickly moving to the power parts. Why? Because velocity triangle, we have seen that when it will hit tangentially, we have seen that we have v1, and then we have u1, and then this is vr1 vr1, and then we have vf1, and then this is that part which is called vw1, right? And similarly at the exit we have vr2, and then we have u2, and then the resultant of this is v2, and then we have vw2 and vf2. This is vw2 and vf2. This is vf2. Okay, so this is the velocity triangle we have already seen. Okay, now what is water power? Water power, we know this is rho qgh. Okay, and runner power, we have seen this is rho q vw1 u1 plus minus vw2 u2. Okay, and what is shaft power? Shaft power is runner power minus of whatever losses we have seen. Okay, so what is hydraulic efficiency? Hydraulic efficiency is runner power divided by water power. So what is runner power? Rho q times vw1 u1 plus minus vw2 u2 divided by rho q gh. So can I say that this is VW1 U1 plus minus VW2 U2 divided by GH. Okay. And what is mechanical efficiency? Mechanical efficiency is shaft power upon runner power. Shaft power divided by runner power. And overall, we have already seen that overall efficiency was hydraulic efficiency into mechanical efficiency, and if volumetric is given, multiplied by volumetric efficiency. Those efficiency things remain same. Means the formula of the efficiencies, means what we have seen in case of Pelton turbine, the same continues here also. Okay. Now, what is speed ratio? Those things we have seen. Na? Speed ratio Ku is speed ratio Ku. This is equal to U1 upon square root of 2gh. Similarly, we have flow ratio. And flow ratio Kf. This is equal to Vf1 upon square root of 2gh. Okay. And then we have width ratio. Width ratio is b1 upon d1, and this must lie somewhere between zero point 0.1 to 0.3. Okay. And what is diameter ratio? Diameter ratio is d1 upon d2. Diameter ratio is d1 upon d2, and generally this is equal to 2. Okay. Now let us understand what is degrees of reaction. So till this point is good enough for you to know. There's no need to understand anything further. But let us go one step forward. So let us understand what is degree of reaction. Degree of reaction. This is equal to total degree of reaction is equal to total change in pressure energy head. Total total change change in pressure energy head head from inlet to outlet inlet to outlet inlet to outlet divided by total total work done per second per unit weight of fluid fluid which is striking per second. Got the idea? What is degree of reaction is what is the total change, right? And what is the total change from in the pressure head from inlet to outlet, and divided by total work done per second. That means that what is the total work done is done by runner power, rotor. So can we write down this one as runner power divided by m dot into g? This we have seen earlier also. So work done per second, we know how to find out. So now my job is to find out what is this value, total change in pressure head from inlet to outlet. So how do we do this? Total change in pressure head from inlet to outlet. So what we will do is that we will apply Bernoulli's equation from inlet to outlet. So what I am doing now is that applying Bernoulli's equation to outlet. So when we apply Bernoulli's equation from inlet to outlet, what we do is that this is P1 upon rho g plus V1 square upon 2z plus Z1. This is at the inlet, okay? And this is equal to P2 upon rho g, means at the outlet, plus V2 square upon 2c at the outlet, plus Z2. And out of this the work is also done, yes or no? From this one part the work was extracted, that means this is equal to the sum of whatever was the at the outlet and plus whatever the work was done. And how do we find out the pressure in total pressure, change in pressure energy head, change in head or pressure energy head, I should say. How do we find out this? This is equal to runner power divided by unit weight, runner power divided by unit weight. So now I know that this is P1 minus P2 upon rho g, P1 minus P2 upon rho g. This is equal to V2 square upon 2c minus V1 square upon 2c. And if I neglect this Z1 and Z2, so this is equal to plus runner power divided by m dot g. Till this point, things are clear. Yeah, this is very important equation. And what is H? This is that H. Yes or no? This is that H. This is that change in H. This is that change in H which is between at the inlet and at the outlet. So when I write down what is degrees of reaction. So degrees of reaction was total change in pressure head from inlet to outlet. So what is that total change? P1 minus P2 upon rho g. So this is that change. So can I write down now the reaction is equal to degrees of reaction is equal to V2 square upon 2z minus V1 square upon 2z plus runner power divided by m dot g divided by runner power upon m dot g. So this is that degrees of reaction. Very important. Okay. So when we solve it further now, so can I write down this one as runner power is equal to 1 plus this G part if you get try to cancel out. So this is 1 plus V2 square minus V1 square divided by 2Z means runner power upon mg this got cancelled out. So 2Z into runner power upon m. And if you what happened? Screen share is ended. Okay. Now visible. Huh? Now can you see? Okay. So V2 is much lesser than V1. We were at this point. Okay. So this degrees of reaction is 1 minus V1 square upon 2Z. And if we expand this term, means rho Q VW1 U1 and divided by m dot G is rho Q, and this G and G will get cancelled out. So the final expression I am writing down, what is that? The degrees of reaction. So your degrees of reaction are is this is equal to 1 minus 1 minus V1 square minus V2 square divided by 2 times VW1 U1 plus minus VW2 U2. Okay. So let us look few things into it. Means whenever you are trying to utilize your kinetic energy at the max, trying to utilize that whatever the kinetic energy you had, it is maximum utilized. Your v2 value should be, v2 value should be as low as possible in order to, in order to utilize the kinetic energy as full. This v2 value should be as low as possible, so as low as possible. So this is only possible, this is only possible why, this is when this is possible means the v2 value will be low. See, at the outlet we have seen the velocity triangle looks like this. So the minimum value of v2 will be this one, yes or no? Why? Because any value, these values, like any v you draw, any v you draw is greater than this v, yes or no? So this value, this v value will be minimum when this is perpendicular to this one. And in that case, this beta value, beta which I show you, that v angle between vw2 and u2, this value will be equal to 90 degree. When beta is equal to 90 degree, the v2 is minimum, and moreover vf2 is equal to 0. No, no, not 0. vf2 is itself is vw2, sorry, vf2 is v2 and vw2 is 0. If this is your absolute velocity at the outlet, then there will be no wall velocity, right? So this vw2 will be directly equal to 0. So when vw2 is 0, then what is the degrees of reaction left now? This r value, this is 1 minus v1 square minus v2 square divided by 2 times vw1 u1. Okay, so what is the runner power? Runner power, we can summarize that this is rho q vw1 u1. If we have information, then only we will use, otherwise most of the time in the ideal case, that the runner power is rho q vw1 u1. Why? Because vw2 is directly 0. And why vw2 is 0? Because in order to utilize the maximum part of kinetic energy, your v2 should be minimum. And when v2 is minimum, it is what? Exiting axially. Okay, so axial exit. So now, based on these facts, let me draw the velocity triangle again, so that whenever the question appears to you, you are able to draw the velocity triangle. So what happens is that this is your v, this is your v1, this is your v1, this is u1, this is u1, and this is the resultant vr1, this is that resultant vr1. Okay, and then we have vf1, this is vf1, and this is vw1. Okay, no, no, not this part. V1 component of v1 is vw1 na? So this is vw1 at the inlet, and this is alpha, means the, this is also called guide vane angle or nozzle angle. Nozzle angle we have seen now, so but in instead of nozzle there are guide vanes, so this is called guide vane angle, and this is theta. And now at the outlet we have, will be having only phi, and this is v2, and this is equal to vf2, this is vr2, and this is u2. Okay, so here your beta value, this is equal to 90 degree. Okay, no, beta we denoted on this side now, so this is beta. Okay, so this beta is equal to 90 degree. So this is the your velocity triangle for the ideal case of Francis turbine. Francis turbines means what? Francis Francis turbine is this is like Pelton. We have seen now that Pelton is impulse turbine. Pelton is impulse turbine. So similarly, we have Francis turbine. This is what? This is reaction turbine. And moreover, what kind of reaction turbine? Radial entry and axial out. No, no. Radial entry and radial outlet. Why? Because this is exiting radially. So this is radial outlet. This is radial outlet. Okay. So we have seen so many things. So now let us move to what? Draft tubes. Yeah. Let us understand draft tubes. And before understanding draft tubes, let us understand few more things. That in this from this velocity triangle, can I write few things? Can I write down that V2 is equal to Vf2? Yes, sir. And can I write down that V1 square is equal to Vw? We know that just now we have seen na, that when we were dealing with the width of the blade. So Vf1 was Vf2. So can I write down reaction degrees of reaction? We saw that degrees of reaction was 1 minus this was v1 square minus v2 square, right? And v1 square just now we have seen is vw1 square plus vf1 square. Okay. And minus we have seen vw2 square, sorry, v2 square, and v2 is nothing but vf2, so vf2 square, and divided by 2 vw1. So when vf1 is vf2, just now I have told you now that for ideal case vf1 is vf2. So if in the ideal case vf1 is equal to vf2, then this vf1 and vf2 are get cancelled out. So now my expression for degrees of reaction is 1 minus vw1 square upon 2 vw1 u1. So can I write down this one as 1 minus this square, and this one got cancelled out. So 1 minus vw1 upon 2 times u1. Okay. In another terms, let us see few more things about it. Have we seen that this vw1 is equal to vf1 cot alpha, or VW1, VW1, VW1 is V1 cos alpha, and VF1 is V1 sin alpha. So VF1 will, let me see, that VW1 is V1 cos alpha. This we understand. And we know that VF1 is V1 sin alpha. So can I write down that VW1 upon VF1 is equal to tan alpha? Tan alpha. So can I write down VW1, VW1? No, this is cot alpha, no? So cos alpha upon sin alpha is cot alpha, right? So cot alpha. So VW1 is VF1 times cot alpha. Can I write? Yes. And can we write down that VF1? VW1 minus U1. So this value I can write down what? VW1. Just give me a second, there's some problem. Okay, there's some problem. Please give me a second. Oh, why this screen share is ended frequently? Now visible, now. Okay. Okay. Oh, I don't know what is the problem. Let me just quickly sign out and I will sign in again.
You are currently the only person in this conference.
Hi. Am I audible first? Okay. Let us quickly start the presentation. Let me share the screen. I hope the screen is visible. Okay. So this point, till this point we have seen. So there's no that much meaning to it, but the derivation part is there. So let me do it. So VF1 cot theta is VW1 minus U1. So now I can write down U1 is equal to VF1 cot alpha, VF1 cot alpha. Why? Because VW1 is VF1 cot alpha. So U1 is VW1 cot alpha minus VF1 cot theta. Minus VF1 cot theta. So now my reaction degrees of reaction is 1 minus, just now we have seen now VW1 upon 2u1, and vw1 just now we have seen is what? Vf1 cot alpha. So Vw1 is Vf1 cot alpha divided by this is 2 times u1, and u1 value is Vf1 cot alpha, Vf1 cot alpha minus Vf1 cot theta, Vf1 cot theta. So this, if you solve, this is equal to 1 minus cot alpha divided by 2 times cot alpha minus cot theta. This is degrees of reaction. Okay. Now let us understand the hydraulics of what? Draft tube. So what is that draft tube? Let me draw first. I told you now that the job of draft tube is to convert this kinetic energy into pressure energy. So at the inlet of the draft tube or at the exit of the turbine, means exit of the turbine is the inlet of draft tube. So at the inlet of draft tube, here you will be having sufficient velocity, but here the pressure is too low. So in order to get dump it into the atmosphere, your pressure should be at least equal to the atmospheric. So in order to convert that, we have draft tube. And what is into this draft tube? Is that first thing is this is your exit, right? This is two. And then we have tail race label. Okay. And then we have datum label. So this is your third, means your datum. Okay. So this is 3 3 is datum. Okay. So this is the difference between these two, y, and this is called HS, means static head of the draft tube. This is HS, static head of the draft tube. Okay. So now I am applying Bernoulli's equation between 2 to 3. So how equation will look like? We know that this is P2 upon rho g we have plus V2 square upon 2g we have plus Z2. This is not Z2. If I have considered this one as datum, then this is equal to, this is equal to P3 upon rho g plus V3 square upon 2g. This is what we have. Okay. And plus no datum label. Okay. So this is 0. So when we solve this, then can we write down this P2 upon rho g? This is equal to P3 upon rho g plus V3 square upon 2g minus V2 square upon 2g minus HS. See, P3 upon rho g means this part, P3 upon rho g at this point, P3 upon rho g, this is equal to what? Atmospheric pressure plus Y. So this is equal to atmospheric pressure plus Y. So I write down this one as atmospheric pressure upon rho g plus Y. So now my P2 upon rho g HS minus Y. So now my P2 upon rho g, P2 upon rho g, this would look like P atmospheric upon rho g minus of V2 square upon 2g minus of V3 square upon 2g minus hs. Why? Because y and y got cancelled. And so can you see one thing, that the runner pressure, this is the pressure at the outlet of the runner. So the runner pressure see that at the exit of the runner we have pressure which is less than the atmospheric pressure. So this is what helping you to increase the net head of this, helps in helps to increase the net head working upon the turbine, working upon the turbine. Okay, so power, this is what makes power and efficiency of the plant given, um, for the given energy input, makes it more efficient and more power output. Okay, why? Because your head is increased now. Why? Because initially in the Pelton turbine you were able to extract between the given pressure and the atmospheric pressure, but here you have freedom to go below the atmospheric pressure even. So that is why the efficiency and the power of this Francis turbine will be high compared to the Pelton turbine for the given energy input. Okay. Now, what is draft tube efficiency? Draft tube efficiency. This is neta draft tube. This is equal to kinetic energy head, kinetic energy head at entry at entry to the draft tube, minus kinetic energy head at exit of the draft tube, exit to draft tube, divided by whom? Kinetic energy head at entry to the draft tube. This is what the efficiency, entry to draft tube. This tells you that this is the amount of energy which has been extracted into draft tube, and what was the total entry? This one. Okay. So neta draft tube is what is the kinetic energy head at entry is V2 square upon 2g, and what is kinetic energy head at exit is V3 square upon 2g divided by V2 square upon 2g. So can I write down this one as V2 square minus V3 square divided by V2 square? Okay. And if there is some head loss in the draft tube, if there is some head loss in the draft tube due to the friction, then we'll have to counter that also. So your neta draft tube would finally look like that. This is V2 square upon 2g. If there is some head loss, this is V3 square upon 2g minus whatever the head loss was there divided by V2 square upon 2g. So this is the efficiency of draft tube. Since questions are not important from this area, but maximum they can go is that they will give you all the informations and they will ask you to find out what is the efficiency of this draft tube. Why? Because they cannot afford to give you so many calculation in one single question. So here what we will have in the form of question is very short part of the questions, and most of the informations will be given to us. Okay. Okay. Now, this Francis part means this was the radial flow turbine. This is done, and next is axial flow. So there is very less difference between axial flow and the radial flow. Let me tell you what is that. And these are called what? Kaplan and propeller turbine. These are axial flow turbines. Axial flow turbines. And what are the types of it? Here we do have one is Kaplan turbine and another is propeller turbine. Kaplan turbine and propeller turbine. So in Kaplan turbine, except the runner position, only the position of runner, and that is it. Other things are same, only the runner means. Here what do we have in the Kaplan turbine is initially what we saw in the case of Francis turbine or the radial flow turbine, that we have seen that the flow was radial. Yes or no? Means flow entered radially and exited. Yeah. Here. Yeah. So here instead of it being radial flow, instead of it being radial flow means the radial flow, what we will be having is the axial flow. So how it would look like, let me show you how it would look like. See, here what we will have is we will have casings. We will have casings. Let me draw the one view of it so that you are clear about that how it looks like. The Kaplan turbine I am drawing. Okay. So Kaplan turbine, how I will show you is only thing which is changed between axial flow and radial flow is that here we have, like, I could have included the image also. So anyway, here we will be having one shaft. Okay, and then on this shaft there will be a boss. Okay, and this boss will have diameters dB, boss diameter, and on this boss we will have runner vanes. We will have runner vanes, and let us say that this is the diameter do. Okay, and then fluid will enter in which direction? Here we will be having guide vanes from here. So what is that? That here we will be having guide vanes, guide vanes, and through these guide vanes, these are the stories, and through these guide vanes the water will flow axially upon it, and similarly from here we will be having guide vanes, and through these guide vanes, let us say that this is that guide vein, and through these guide vanes the water will flow axially upon the upon what? Upon this boss or the shaft. So once the uh, what do I say? That once the flow is established, here we will be having n number of blades fitted like this. So what we can see here is that the water is uh, entering in the axial direction. Yes or no? This is the axis of shaft. Yes or no? So this is finally this will get rotated. Okay. So can we see that water is running entering into the axial direction of the shaft? So that is why this is called axial flow turbine. Okay. And what are the types we have seen? One is propeller and another one is Kaplan. So when the vanes are fixed to the hub and not adjustable, then these are non propeller turbine. In the propeller turbine, sometimes the questions might appear like this, that here in the propeller turbine, vanes are fixed, vanes are fixed, and means fixed means they are not adjustable. Okay. And here what we do have in the Kaplan turbine, here the vanes are adjustable, vanes are adjustable. So what do I mean? What do I mean? That here we have n number of vanes fixed on a shaft. This is the shaft. So here we have n number of vanes. So those vanes may be fixed or maybe not fixed. So if they are fixed, that means that you cannot change the area of the flow. Yes or no? Once they are fixed, then they are remain constant. But if they are adjustable, means let us say that if this is the vane, like how it looks like is that there is a shaft. Okay. And on the shaft there are veins like this one, like this one. So what happens, that if these veins are adjustable upon this boss, then what you can do is that you can make it closer to this area or you can make it outwards. That means that you can change the area of the flow. And if the, how why we are doing that, in order to load, like let us say that if the load is less, then why do we need to produce unnecessary energy? So in that case, if the vanes are adjustable, we can reduce the area flow. Similarly, if the loads are getting higher, then what we can do is that we can make it wide so that flow rate is increased. Okay. So what will be the discharge here? The discharge here will be between this part, means can I write down discharge thing directly? The discharge q discharge q or area of flow directly. Area of flow, what is the area of flow? This is equal to pi by 4 into, can I write down this one as d outer square minus dv square? D outer square minus dv square. This is the area of flow, right? And what is the discharge value? Discharge value, that q is area of flow into velocity of flow. And what is area of flow? This is pi by 4 into d naught square minus dv.
You are currently the only person in this conference. You are currently the only person in this conference.
area is remaining constant. This charge area is remaining constant. That means flow velocity components are bound to remain constant. So can I say that this vf1 value will be vf2 value always? Okay. Why? Because area of flow, this area also, in this case also, what do we see is that beta value which we have seen now, means the angle between what v2 and vw2, this remains 90 degree here. So beta, if beta is 90 degree, then again in this case also vw2 will be 0. If beta is 90 degree, then vw2 value is 0, 0. So everything remains same as per turbine or radial flow turbine. Only change what we are is feeling here. I am telling you that first thing is that vf1 is equal to vf. You can find out v2 also. Why? Because v2, when it is 90 degree, there is no world component, right? So vf2 and vf2 will be equal, and we know that vf1 is equal to vf2, which makes vf1 is also equal to v2. So one thing is done, and second thing is u will also remain same. Why? Because u1 is equal to u2 is I.
You are currently the only person in this conference.
Calculated. Can you see the screen? Okay. I don't know why there is frequent problem today. Okay. So u1, u1 is pi times d naught into n by 60. And what is u2? u2 is pi times db into n upon 60. But I told you that this dm value is d naught plus db divided by 2. Okay. Okay. So every calculation, means whatever calculation we will be doing here is nothing but as per the Francis turbine, means calculations are as per the Francis turbine. Calculations are as per the Francis turbine only. Only thing what we are going to change here, that is nothing but is what is u value. So what we will do is that we'll stop here and we'll solve questions based on Francis and Kaplan tomorrow, and we'll see the unit quantities and model prototype relationship also. Okay, so mostly theoretical part is done. Only few things are remaining. So tomorrow we'll be able to finish. Okay. So I don't know why today is frequent connection disconnection also. So we'll do that on tomorrow. Okay.